Learning outcomes. After studying this module, you shall be able to know the difference between the spinning and the orbital motion of the electron. You will analyze the various free ion terms for different configurations. You will also learn the various factors that influence the spin and orbital motion. You will understand the orbital in an atom along with its orbital motion. For the multi-electronic atoms and ions, the spin and orbital motion of various electrons are coupled together by spin-orbit coupling, which is also called LS coupling or Russell-Saunders coupling. In this practice, the total angular momentum represented by the capital L and the total spin angular momentum represented by capital S combine together to generate a new set of quantum number suggested by the capital J.
Spinning of an electron. A spherical body rotating about a fixed axis that passes through a point at the center of the sphere represents a model that how electron behaves inside an atom. This means an electron always spins on its own axis either in a clockwise or anti-clockwise direction. The concept was first introduced by Uhlenbeck and Goudsmit. The spinning of an electron about its own axis gives rise to spin quantum number represented by ms. It is required to fully specify the ambience of an electron in the atom. The spin quantum number can have two values, plus half if an electron is spinning clockwise and minus half if it is rotating anti-clockwise. This spinning of an electron generates an intrinsic angular momentum related to it. The splitting of many spectral lines in the electronic spectra can be analyzed with the presence of spin angular momentum. An electron gyrating about the nucleus experiences the magnetic field produced by the nucleus, which is circling about it in its own casing. This magnetic field then operates upon the electron's own spin magnetic moment to create substates in terms of energy. The angular momentum of a spinning particle is mathematically symbolized by a vector as represented for the electronic spin. Vector length is given by s multiplied by s plus 1 whole raised to the power half, where small s is the spin quantum number. The vector can acquire only certain values representing specific orientations in this space. In case of multi-electronic systems, the spin momentum of various electrons coupled together to give a vector sum represented by the symbol S. Associated with capital S is ms, which represents the magnitude of orientation of the spin. In simple terms, S is the quantum number associated with the length of the total spin and ms is the quantum number associated with the orientation of total spin relative to the z-axis. Therefore, the possible values of ms can be s, s minus 1 and up to minus s. Orbital motion of an electron. First of all, we will define what is an orbital. An orbital can be suggested as a space around the nucleus where electron can move around. Since, due to uncertainty in determining the velocity and angular momentum persist for any electronic movement, an orbital can better be discussed in terms of probability. Hence, it is that path surrounding the nucleus where the probability of finding the electron is maximum. This has been depicted. Since the electron shows dual nature, it behaves as particle and also as a wave. Hence, the electronic movement can be represented in terms of a wave function and a wave equation. Talking in terms of polar coordinates, the wave function splits into two parts, namely radial part and the angular part. The radial part gives an idea about the probability of finding the electron at a distance r from the nucleus. In case of a radial node, the radial part of a wave function changes sign, and when we have an angular node, the angular part of the wave function changes sign. The number of nodes in an orbital is given by the total number of angular nodes will be equal to L, and the number of radial nodes will be equal to n minus 1 minus L. Total number of nodes will now be equal to n minus 1. The various atomic orbitals represented in an hydrogen atom. Next, we are going to define orbital motion. Classically, rotational motion refers to the rotation of an object about a fixed point. An electron in an atom moves in a circular path with the fixed radius about the nucleus. This rotational motion of an electron in an orbit around the nucleus leads to the origin of orbital angular momentum. Orbital angular momentum can be visualized in terms of electron with mass m revolving around the nucleus in an orbit of the radius r and the angular velocity v. The expression is now given as capital L is equal to m into v into r, where capital L is the angular momentum of the system. The orbital angular momentum can be represented by a vector. The vector representation of the electron rotating in the Bohr's orbit. The angular momentum vector is always directed towards the direction where it is perpendicular to the plane in which circular motion of the electron in its orbit is taking place. Angular momentum is represented by the vector length. The important features in the case of classical representation for the angular momentum are given as: first, the angular momentum can be represented by a vector whose direction is related to the sense of the direction of the rotation. Next, It can also be a representation of the vector which can be conveniently placed on the axis of the rotation, and that the length of the vector is directly proportional to the absolute magnitude of the angular momentum. In case of multi-electronic systems, the orbital angular moments of various electrons couple together to give the resultant orbital angular momentum of the system. Thus, the total angular momentum quantum number given by capital L can be represented as capital L will be equal to small l 1 plus small l 2 up to small l 1 minus small l 2. The quantum number capital ML describes the component of L in the direction of the magnetic field for an atomic state. The values of L correspond to the atomic states which can be described in terms of S, P, D, F, and so on. Next, we are going to discuss spin-orbit coupling. First of all, we should understand what is spin-orbit coupling. The electrons in an atom behave in a very similar manner in the sense of having an orbital as well as spin motion. Till this point, we have seen that the orbital as well as spin motion of various electrons in a system have to be added so as to give resultant total orbital and spin angular moments. Now we will see that the spin and angular moments of the electrons also coupled together by the process called spin-orbit coupling. This coupling further gives rise to a new quantum number deciphered as capital J, which is called total angular moment quantum number. The quantum number J can have the following values. Capital J will be equal to capital L plus capital S up to capital L minus capital S. Next, we will discuss free ion terms. The atomic states characterized by the values of L, S, J are referred to as free ion terms or Russell-Saunders terms. This is because they actually describe the individual atoms or ions which are ligands free. They are also specified as term symbols. Term symbols are represented in the form where capital L is designated along with the value of spin multiplicity on the left superscript and value of J on the right subscript. For example, the term symbol triplet P2 represents the state in which capital L will be equal to 1 corresponding to P and the spin multiplicity will be equal to 3, whereas the value of J will be 2. Free ion terms are very important in the analysis of the absorption spectra of the coordination compounds. Spin-orbit coupling acts to split up free ion terms into states of different energies. For example, triplet P term splits up into states of 3 different energies as can be seen. A single electronic state can give rise to various free energy terms and term symbols. These terms have different energies which further suggest the difference in electronic interaction for the different terms. For example, P2 configuration can have three different free ion terms which are distinct in terms of their energies. Various free ion terms for which electronic configurations of the d orbital have been given. In order to find a term of lowest energy, following rules need to be followed. The first rule is the ground state is the one with highest spin multiplicity. According to the second rule, if two or more terms have the same value of spin multiplicity, ground state is one with the maximum value of total orbital angular momentum quantum number, which is represented by capital L. For example, as given in table, for D2 configuration, it has two terms with same spin multiplicity of 3. These are triplet P and triplet F. Out of these terms, triplet F will be of lower energy since it has a greater value of L. According to the next rule, for the subshell, there are less than half-filled electrons, then the state of lowest J value is the term of lowest energy, and for the terms that are more than half-filled, the term with the maximum value of capital J is the one with lowest energy. For example, in case of P2 configuration, the term triplet P0 will be of lowest energy. In order to interpret the electronic spectra of the coordination complexes, it is often required to find out the term of lowest energy. Given below is an example of D3 configuration in an octahedral geometry. The various steps involved in the procedure are as follows. First of all, we are going to represent the valence electrons in various energy shells. According to the D3 configuration, next step will be to calculate the total number of unpaired electrons. In this present case, it is going to be 3. Therefore, the spin multiplicity will be S is equal to 3 by 2. The spin multiplicity will be given by 2 into 3 by 2 plus 1, which will be equal to 4. Now we will find the maximum possible value of ml, which will give the value of capital L. In this case, the maximum possible value of ml will be the one that we will get by adding the small l values of the individual electrons. Therefore, the maximum ml value will be equal to 2 plus 1 plus 0, which is going to be equal to 3. This value corresponds to the F term. Now, the lowest value of J in this case will determine lowest energy term since the shell is less than half filled. Therefore, the value of J will be equal to 9 by 2, 7 by 2, 5 by 2, 3 by 2. In this case, the lowest energy term will now be the J value of 3 by 2. Therefore, the complete term symbol of the lowest term can now be depicted as quadrat F 3 by 2.
Electron always spin on its own axis either in the clockwise or the anti-clockwise direction. This spinning of electron gives rise to the spin quantum number, which is represented by ms. The spin quantum number can either have the value of plus half, which suggests that it is spinning in the clockwise direction, and minus half, which suggests that it is spinning in the anti-clockwise one. Spinning motion of an electron gives rise to the intrinsic angular momentum associated with it. The splitting of many spectral lines in the electronic spectra can be analyzed with the presence of spin angular momentum. The angular momentum of a spinning particle is mathematically symbolized by the vector. For the electronic spin, vector length is represented by s into s plus 1 whole raised to the power half, where s is the spin quantum number. The total angular momentum revolving in a circular path can be represented by a vector. In case of multi-electronic systems, the orbital angular momentum for various electrons couple together to give the value of resultant orbital angular momentum for the system. Spin and angular moments of the electrons also couple together by the process known as spin-orbit coupling. This coupling further gives rise to a new quantum number J, which is called total angular momentum quantum number. Term symbols are represented in the form where capital L is designated along with the values of spin multiplicity on the left subscript and value of J on the right subscript. The total term symbol can be represented as 2s plus 1 capital L J. A single electronic state can give rise to various energy terms and term symbols. These terms have different energies, which further suggest the difference in electronic interactions for the different terms.